So thanks a lot for the invitation and the nice introduction of me. So I think I joined Clermont IV and not Clermont V, I remember. So I think Clermont IV is the latest European program for polaritons. Okay, so it is a great honor to talk about our work in this seminar. So this work is based on the cooperation between the experimental team in Tianjin University and the theoretical team in Paderborn University. Tianjin is a city which is not very far from Beijing. So if you check the high-speed train in China, just needs a half hour. Tianjin University is one of the two biggest universities at Tianjin. I think another university, maybe more famous, is Nankai University. The motivation of our experiments is based on your seminal work in science, where you realize synthetic spin-orbital coupling on cavity photons. Spin-orbital coupling plays a very important role in spin optronics and topological insulators. Also, synthetic spin-orbital coupling has been realized in cold atom condensate or cold Fermi gas. In this work, what we wanted to do is to check whether strong coupling can occur or not if we insert semiconductor layers into the liquid crystal macrocavity. To be further, we also want to see whether polariton condensation can be realized or not, which can be tuned as external voltage due to the Rashba-Dresselhaus effect. We select semiconductors and multiple kinds of semiconductors. Perovskite grouped material can sustain excitons with a huge exciton bedding. And material as the cavity layer. However, polariton condensation and Rashba spin orbital coupling has not been realized yet. Fortunately, other perovskites can offer to realize polariton condensation at room temperature. Being transferred into the macrocavity, inorganic perovskite-based polariton condensation has been realized at room temperature. Also, perovskite can be loaded into periodical potential lattice, where one-dimensional band structures due to the coupling between the potential sites can be observed. So these results show that the perovskite can be used to study a strong lattice-matrix interaction at room temperature in a well-controlled manner. So it is highly possible that strong lattice-matrix interaction can be realized if we insert perovskite macroplates into the liquid crystal macrocavity. We designed the liquid crystal macrocavity by using the transfer matrix method. Firstly, we do not consider the anisotropic refractive index of the liquid crystal layer, and just assume that the refractive index of the cavity layer to be around 1.5. In this macrocavity, we put the perovskite material onto the surface of the bottom DBR with the center wavelength of the stop band at around 530 nanometer. From the calculation, we can see that the electric field here can reach local maximum at the position where the perovskite macroplate is inserted. In addition, our calculation shows that the strong coupling can be realized due to large exciton bending energy and oscillator strength of the perovskite microplates. The perovskite microplates are grown by the CVD method using some powders under the flow of the inert gas at high temperature. This graph shows the perovskite microplates after the growth, where we can see the size of the perovskite varies from several micrometer to maybe around 20 micrometer. The thickness of the grown perovskite microplates is not a constant, which varies around maybe 200 to 400 nanometer in our experiments. So this is the experimental setup we used. We firstly measure the reflectivity of one bare perovskite microplate, and we can get a similar dispersion as the Savvidis group, which show clear strong coupling in the perovskite microplates. The thickness of this selected perovskite microplate is around 200 nanometers, so we do not observe the anisotropy of the perovskite itself. To fabricate the liquid crystal microcavity, firstly, we transfer the perovskite microplates onto the bottom DBR and paste the top DBR to form the empty microcavity. Finally, the liquid crystal molecule is filled into the cavity, where the molecular orientation can be controlled by the external voltage, which is applied onto the SU surface of the DBRs. Up to now, polariton lasing based on perovskite microplates cannot be realized under CW optical bonding. The excitation source we use is a commercial 5 femtosecond laser with the wavelength of around 400 nanometer and the repetition rate of 6,000 hertz. The size of the laser spot is around 60 micrometers, which is much larger than the perovskite microplate. First thing we want to discuss is the large curvature dispersion in the perovskite microcavity, which has been observed several times by other groups like Schwinn-Schwarz group. We believe the reason for this kind of dispersion is the scattering of photons out of the perovskite microplate, which just follow the cavity walls and do not couple with the excitons. Here we can see the curvature the curvature of these modes is much larger than the lower branch polariton. In our experiments, we can also observe similar large curvature bands under 0 voltage. If we select the area near the perovskite microplate and measure the dispersion for this area, we can only observe the cavity modes, which do not couple with the excitons of the perovskites. The coexistence of these two kinds of dispersion cannot be observed in a weak coupling microcavity, which we plot in the red graph. Here we fabricate a new liquid crystal microcavity where WS2 monolayer is inserted in the cavity layer. The structure of this new microcavity is the same as the perovskite microcavity. In this new microcavity, only weak coupling between the excitons of the monolayer and the cavity modes is observed. In this case, we can see that the dispersion of the monolayer area and the other area is the same. So these results clearly show that a strong coupling between the perovskite excitons and the cavity photon modes are observed in our microcavity. And the existence of this large curvature dispersion can be used to prove the existence of strong coupling within the microcavity. So in the following, we just focus on the lower branch polaritons of the microcavity. We measure the dispersion of the macrocavity when the laser bumping density is below threshold. We observe several sites of modes LP1 to LP4, which have different curvature due to different detuning with the exciton residence. When the modes are closer to the excitons, the dispersion curvature is smaller. I think this is the signature of the strong coupling within a long cavity length macrocavity, which can sustain several cavity modes. Of course, the curvature of these polariton modes is much smaller than the cavity modes we discussed in last slide. We fit this polariton dispersion by the coupled oscillator model, where we can get the rapid splitting and the detuning for all these modes. The rapid splitting we obtain is around 90 milliliter, and the detuning for the lower branch polaritons LP1 to LP4 are listed here. The Hopf field coefficients for these polariton branches are plotted here. We can see that the cavity photon components increases from LP1 to LP4, which is consistent with the curvature of these polariton modes. Increasing the pumping power large enough, we can see the integrated intensity of the initial light from the perovskite macrocavity increases superlinearly with the bumping density, and the line width increases reduced greatly at the threshold. During this process, we observe continuous energy blue shift of the polariton modes. We note that the polaritons condense at the ground state of the LP4 with the threshold which is smaller than the mode density. So these experiments, we believe, clearly show that polariton condensation occurs in our perovskite macrocavity. To make sure polariton condense in the strong coupling regime, firstly, we replot the dispersion above threshold in log scale, and we compare the dispersion with the below threshold. Here we can see that the dispersion at large momentum above threshold is the same as that below threshold. This indicates that we do observe the polariton condensation in the strong coupling regime. Under higher power, polariton can condense at LP3 and LP4 at the same time. Further increasing the bumping power can destroy the perovskite macroplace. We hope two thresholds can be observed if the quality of the perovskite macroplace is improved further. Secondly, we also check whether polariton condensation occurs or not in the strong coupling regime by other method. Here we add a very weak CW laser, which is focused onto the center of the femtosecond laser, where we observe polariton condensation. In this case, the interaction between the injected exciton reservoir by the CW laser and the polariton condensation created by the femtosecond laser can induce noticeable energy blue shift. In the experiments, we do observe energy blue shift when the power of the CW laser is very small, for example, 50 microwatts. So I think if the lasing occurs in the weak coupling regime, we should not observe energy blue shift, only if the bumping density of the CW laser is very large, which can induce changes of the refractive index of the cavity layer. So from above results, we believe we do observe polariton condensation in the strong coupling regime. Polariton condensation should be accompanied by the build-up of the macroscopical coherence. We measure the macroscopical coherence of the polariton condensate by building a macroscene interferometer, where one arm is rotated by 180 degrees. The interference fringes are clearly observed above threshold, which confirms that the macroscopic coherence has been built up above threshold across the polariton condensate. The external voltage applied across the macrocavity can tune the polariton modes both below and above threshold by controlling the orientation of the liquid crystal molecular director. This graph shows the dispersion of the macrocavity as a function of the external voltage below threshold. We can observe clearly X-ray splitting when the voltage is 3 volts. Increasing the voltage will move the horizontally linear polarized lower branch polariton branches, where the vertically linear polarized polariton branches is fixed. So the energy difference between these two sets of modes is decreased, showing the same behavior as the cavity modes in your science paper. When the two lower branch polariton branches with the opposite parity and also general linear polarization come into resonance at the voltage of around 4.5 volts, the Rashba interaction will shift the two polariton branches apart along Kx direction. When the voltage is larger than 4.5 volts, we can see that the two branch polaritons are split again. So similar effects can be observed on our threshold, where polariton condensate can be tuned by the electric field. Before and after 4.5 volts, we can see that the two branches with opposite parity and also general linear polarization are either approaching or rebelling with each other. Under the voltage of 4.5 volts, the two modes are degenerate and they are shifted along Kx direction, depending on the polarization. In addition, we found that the polariton condensate is very sensitive to the external voltage applied across the macrocavity. For example, the LP4 condensate cannot condense when the voltage is larger than 5.5 volts. The reason for this, we believe, is that the voltage on the macrocavity modifies the electric field distribution in the cavity layer. So in this case, the external voltage directly allows us to manipulate the population and the threshold of the polariton condensate. I believe this is very challenging to be realized in common macrocavities. So if we measure the polarization of the dispersion, we can see that when the voltage is 2 volts, the dispersion of the perovskite macrocavity show clearly X and Y splitting. The Rashba-Dresselhaus effect can be observed when the voltage is 4.5 volts. In theory, we use this model, which is developed by our collaborator, Mashika and Stefan, in the I think it is circular polarization basis. Here, Ex is the exciton energy, and for different spins, I think they are the same. We assume the two cavity photon modes are near resonant, which are denoted by EP, and have the same effective mass. The two cavity photon modes are perpendicularly linear polarized and have different parity. The former leads to that they can strongly couple to their corresponding excitons with the coupling strength of omega, and later leads to the Rashba-Dresselhaus effect with the spin splitting spins of epsilon along Kx direction. Beta 0 denotes the X-ray splitting, and beta 1 represents the TE TM splitting. Phi is the polar angle with the range from 0 to pi. So we can see that the theoretical curves agree with the dispersion, experimental dispersion, I think very well. Okay, finally, we measure the spin polarized momentum space and real space matches above threshold when the voltage is 0 volt and 4.5 volt. It is clear that the polariton condensate with the opposite spins is split both in the far field and near field at the voltage of around 4.5 volts. The two spin components of the polariton condensate gain non-zero momentum, and the polariton condensate is split by around 0.8 micrometer. So these results clearly show the Rashba-Dresselhaus effect on the polariton condensate at room temperature. In a smaller perovskite microplate within the same microcavity, we can observe polariton condensation with discrete energy levels due to the finite size of the sample. Here we observe two discrete energy levels when the voltage is 0. One energy level is the ground state, and another level corresponds to one of the dipolars. And the voltage of 4.5 volts, we can see both the ground state and the higher order polariton condensates are split by the Rashba-Dresselhaus effect in the far field. Based on this, we can investigate further like the bistability or multi-stability using this smaller size perovskite microplates later. Okay, in the future, we are planning to study whether strap phase of polariton condensate can be observed or not. In the cold atom condensate, strap phase has been measured by predicted and measured by using Raman lasers. Now the problem for our microcavity is that the condensed polaritons seems to be localized at a small region of around 5 micrometer. Our next step is to improve the quality of the perovskite microplates. Another direction is the anisotropy of the perovskite, which we do not observe in the present experiments. It looks that when the thickness of the perovskite microplate is large enough, like several micrometer, the Rashba effect can be observed in a single microcavity without liquid crystal molecule. So if we can fabricate a thicker perovskite microplate, it is interesting to study like how affect the polariton modes with this kind of Rashba effect just due to the anisotropy of the perovskite microplate itself. Okay, to summarize, we realize exciton polariton condensation in our perovskite microcavity filled with liquid crystal at room temperature. This liquid crystal acts as a synthetic gauge field on the polariton condensate. Thus, polariton condensate with opposite spins is split in both the far and near field. We believe our work offers to study non-trivial bands for polariton condensate at room temperature in the future. Finally, we want to thank the funding, the National Science Foundation of China and some funds from Germany from our collaborator. Okay, thanks a lot.
Thank you very much, Tingge. So yes. I will try, we have several speakers now. There are 40 participants on this call. So I will try to coordinate the question sessions. So if you have a question, please raise your hand. And if you know how to do. Yes, so we have first question by Tamsin Cookson. Tamsin, please unmute your microphone.
Hello, thank you for the nice talk. I was wondering, in the condensation which is above threshold, you have horizontal lines throughout the, here, the back a slide, or forward.
This one?
The previous, no, the other way, sorry. I wasn't sure which way you were going.
You mean this one?
No, it's when it's above, you can sort of see it here on LP4, but when it's above threshold, not below. You see sort of horizontal lines in the dispersion PL, particularly here on LP4.
Oh, you mean this?
Yeah, you get these horizontal lines throughout the LP4 dispersion, and I was wondering where they originate from.
Sorry, you mean in above threshold in log scale, you see some lines, right?
Yeah, the horizontal lines throughout going across the dispersion. Yeah.
I think this line is, you can see the dispersion here. We already see the discrete energy levels here. So I mean, because the size of this perovskite microplate is around maybe let me see, maybe 50 micrometers. So below threshold, we already see this discrete energy levels. So above threshold, we believe maybe both the ground state and some high order modes are I think condensed, but the energy difference is too small, so we cannot observe. It's beyond our experimental resolution. From our spectrometer, I think. So this one.
So it's intrinsic to the nanoplatelets and not anything to do with the liquid crystal or any sort of self-interference within the cavity or anything?
No, I think it's due to the perovskite microplate you can see here, I think.
Mm-hmm.
Yes, you can see, sorry, because these lines, the fitted lines, but I think it's really, because, in the experiment, we observe really, there, this discrete energy levels here already appear for LP4, I remember, I think here. So I think it's like, if we have a better, spectrometer, which have, larger resolution, we can resolve these modes, I think. Sorry, here.
And then the second part of the question was, what do you see these discrete modes in LP1 or LP2 when you get them to lathe further on?
No, we do not see lasing from LP1, LP4. So in the experiments, usually we can see the lasing. Here, I think it's around. We see this is LP4, and this one should be LP. No, because the voltage is 3 volts. Sorry, I mean the voltage here for this battery is 3 volts, and the dispersion here is the number is 2 volts. So sometimes we see other branch, like here we can see this is lower branch LP5. So above threshold. So I think it's we do not see lasing, with a higher energy and under exciton component. Usually we see lasing on LP3 and LP4. But if we choose other perovskite microplates which have different thickness, maybe we can see. We will try. Maybe I think they will lasing at a higher energy level, like here, I think.
Okay, thank you very much.
Okay, next question comes from Helgi Sigurdsson.
Hello, can you hear me? Yeah. All right. Thanks a lot for a really nice talk. This is really interesting. So I have a question. I don't think it was mentioned in the presentation, but I was reading the paper the other day, and it appears several times that you are realizing an artificial gauge field in this system. Is that correct?
Yes. So I think we mentioned the synthetic gauge field is like, here it's like we need the dispersion with different spin polarization is shifted. I mean, depending on their polarization. I mean, here it's like some synthetic policy, like synthetic magnetic field, like we can shift the dispersion. I mean, depending on their polarization here.
Right, but that's effective magnetic effect. But I think the criteria to have an artificial gauge field is that you have to be able to write a 2-level Hamiltonian in something that's called the minimal coupling formalism, where you introduce the canonical momentum with the vector potential of your artificial gauge field. And to my knowledge, this is only possible at something like Dirac cones, where the dispersion becomes linear. So, and because all your dispersion spheres are not crossing, they're all split in energy, I'm just not so sure that there is any artificial gauge field in the system. There is a fake magnetic effect, but not an artificial gauge field.
Okay. Sorry. I mean, I agree with you. So here it's like, because the spectrometer, I mean, the resolution of our spectrometer is limited. So here, it's I mean, the splitting of this dispersion, it's not I mean, it's not how to say. If we took the, it's like it's not very clear. But I think really I agree with you. You know, because the present results we will how to say, we will investigate later. I mean,
Okay.
but from here we can see here from this one. I think with the result, you know, here you can see this is you know, look. I mean, this is the low branch polaritons, but it's I mean, it's the same result. I mean, it's look very similar to the, you mean to the science paper, I mean, about the liquid crystal microcavity here.
Okay, all right. Thanks a lot.
Thank you, Helgi. So next was Gabriele Raino from ETH.
Hello, good morning. So first
Hello.
of all, thanks for sharing these beautiful results. I do have a question on the material itself. So your platelets are quite thick, right? 100, 200 nanometer, and
Yes.
they are very large, let's say. I do not expect any quantum confinement. So, and the bonding energy in bulk cis-simulated bromide is quite low. We are talking about 30 millielectron volt. How you expect to have a stable exciton at room temperature in these bulk materials?
Sorry, you mean I cannot follow you. You mean the size of our perovskite microplate is
it's quite large, right? I imagine this as a bulk material. There is no quantum confinement acting on the energy levels. So it's the way I see it's very large piece of cis-simulated bromide crystals, right?
Okay. So you mean yes. The size is I think it's around you know, smaller. You know, I think it's around around 20 megameters. So could I ask you, your question is
I do not expect excitonic properties at room temperature for such large crystals. So, for example, I rephrase my question. In the absorption of these materials, do you see excitonic bands, or is just uncorrelated electron pair there?
I see. I think it's really. I mean, if we measure just a single perovskite microplate, we can clearly see, you know, the similar results. I mean, as symmetric group, which I think this one clearly shows this is strong coupling between the excitons and the cavity photomoles. Also, sorry, as I do not list some reference. I think even like this paper, I think, sorry, this one. In this paper, I think the thickness is even larger than ours. It's around 5 micrometer. I mean, the thickness of the perovskite microplate is 5 micrometer, but really they also observe strong coupling. I mean, so I think that definitely we have exciton resonance in this material.
Okay, thank you.
Thank you, Gabriele. So let's move on to Barbara Pietka from Warsaw.
Yes, thank you. Thank you. Thank you very much for a nice talk. I have a question concerning the blue shift, because if you could come to the slide where you have the blue shift together with the line width narrowing. Yes, exactly here. So they're at the pump fluence of 20. So exactly when you have your threshold, then the blue shift saturates. So my question is, how would you distinguish from the interaction and the loss of the strong coupling here?
Thanks. This is a very good question. You know, in our microcavity, the highest power we can increase is around 80 microjoule per square meter. But if we increase the power further, like larger than the mode density, what we see is like the emitted light intensity from our microcavity is reduced. So we believe if the power is larger, really, I think the perovskite microplate is destroyed. So as I discussed in my presentation, we are working to improve the quality of the perovskite. So we hope in a better perovskite microcavity, we can observe, the collapse of strong coupling, or even up to now, I think the power density we can use is limited by the quality of the perovskite. So I think in this process, I think from the power range we measure, I think we believe it is always in the strong coupling regime. From this one, I think like we measure the dispersion, and check the dispersion at large momentum. I think we do not see any changes compared with the dispersion below threshold.
Okay, thank you. So next is Paul Easton from Dublin.
Hi, thank you very much. And actually, thank you everyone for the opportunity to say hi and to hear about all this interesting stuff. It's lovely to see you all, many of whom I know from a long time ago. I had a perhaps slightly philosophical question coming back to this issue of gauge fields. It seems to me that what you've got here is really half of the physics of a gauge field, that the polaritons motion is changed by the applied field, the polarization dependence, but you don't have the reverse effect that the polaritons affect the liquid crystal and therefore change the effective field, which is what happens really if you have charged particles in a magnetic field. So I guess my slightly crazy question is there any prospect in polariton systems like this of having the liquid crystal affected by the polariton state and therefore bringing back kind of both sides of the physics of gauge fields?
Thanks. In my presentation on our paper, we mentioned the synthetic gauge field is really is follow the claim of the science paper. Because the polariton, inherent the synthetic spin orbit coupling from the cavity photomos, with this liquid crystal cavity. So I'm not sure yet, but I think if we can to fabricate some specific structures of the perovskite microplates, maybe we can, but I'm not sure. But we are not sure. In our present results.
Okay, thank you.
Thank you, Paul. Next question is from Anton Zassedateliev from Austria.
Well, thank you very much for the nice talk. It was very interesting to hear. I had a question actually about follow-up question to exciton transition. Could you specify approximately the dephasing time of your excitons on this material?
Sorry, you mean
the phasing time, yeah, of excitons.
You mean the excitons, right?
Yeah, the width of your exciton peak, for instance. Full width of at half maximum.
Sorry, you mean you want to ask is how we characterize the excitons of this material, right?
Yeah, I'm just wondering if you can give us some number of the bits of at full width of maximum for excitons or at your perovskite slabs.
Sorry. You mean this kind of material? You mean the excitons?
Okay. Let me see here.
Yes, it's here. In the body energy of this,
what's the gamma? The dephasing time of exciton?
Sorry.
Okay.
You mean the dephasing time of excitons of this material, right?
Yeah. Exactly.
Sorry. We have not started to investigate the exciton dephasing time of this material. So we are because first we want to improve the quality of this perovskite, because sometimes really we can see this kind of perovskite is very fragile if we increase the bonding power further. So firstly, we will improve the quality of this perovskite, and we will start to call the exciton diffusion time and other properties of the exciton, like the lifetime and other other properties. And up to now, we have started to focus on the basic exciton properties of this kind of material.
And just in my view, it is essential to know if you're talking about strong coupling, because you need to, relate this number to your Rabi splitting, right? In order to be sure that you have the strong coupling. By the way, what's the Rabi splitting in your case? How big is that?
It's 90 milliV here. The Rabi splitting for this kind of, cavity is 90 milliV. So, it's not very large. Another thing is like it looks like the perovskite microplate we grow is not very homogeneous. So that's why the size of this perovskite microplate is around 50 micrometer, but we see polariton condensing area is around 5 micrometer. Is small area. So this is the one problem of this kind of material in our group.
Okay, thanks. Also, very good that you stop here. I also had a question. Just you remind me. How can you, probably I missed this point. Can you elaborate a little bit how you actually how you interpret the fact that your model at the high K vectors at the high angles? Go back, please. Go back to this slide. Your model, the polariton branches are different from the wings of the high K parts of your dispersions. There is a discrepancy here. How you interpret this? Probably I missed this.
Sorry, you mean this? This is
no, go down a little bit.
This one?
And the left, yeah, left. Okay, a bit high, please. So LP1, there is LP1.
Yes,
it's written here, yeah, and there, see there is a very faded wings going on.
Oh, this one.
Yeah, these two. Yeah, how?
Oh, sorry. This one and this one is the I think the cavity mode, which I did here. It's like this one. Sorry. So this is the cavity mode, cavity photo mode, and this like this one. So this I think is something many groups observed in the experiments for the perovskite cavities like this. So you can see the curvature of this mode definitely is larger than the lower branch and this one. So the reason for the appearance of this modes, we believe I think is like it's the signal coming from out of the perovskite. So they do not couple with the excitons. So we also see this one here. So this one is a large curvature dispersion.
Oh, all right. So it just looks very nice, like an extension. But I get the point. Okay, nice. Yeah, and also have a question regarding the mechanisms of the condensation in your system. Can you elaborate a little bit? What are the mechanisms, the main mechanisms to condense particles in your system?
You mean the mechanism for condensation?
Yeah.
The mechanism for condensation. You mean the sorry? You mean the mechanism? You mean why?
Yeah, exactly. How do they condense particles, the polaritons in the system? So, for instance, in the inorganic systems, we know that there's based on acoustic photons and polariton scattering process. But in your case, it could be different. I don't know.
In our case, we think the mechanism for the polariton condensation is the same as other semiconductors like gallium arsenide. And other.
Do you think the same mechanism? Yeah.
I think so. Because the advantage of this material is like the eddy energy and oscillator strength. of the exciton is very large compared with other materials. So we can see condensation, at room temperature much easily. Like in this work, like in this one, they also observe condensation of similar perovskites. I think it's the same.
Mm-hmm. And do you know, just top of your head, probably where is the gain? What's the energy, the photon energy of the gain of your perovskite lab? Just the gain. I mean, if you weakly coupled, where would you expect the lasing, for instance? Where is the gain maximum of the material? Optical gain maximum.
You mean the
if you do AC, for instance, amplified spontaneous emission on your material, where would you expect the maximum of the AC, for instance?
You mean the maximum gain, right?
Yeah, exactly, gain, optical gain.
In this, I mean, we measure the care of this material, and without microcavity. Firstly, we found that it looks like very easy to lasing. I mean, if we do not put the microcavity, so I believe the lasing wavelength is really, I mean, for the size we grow, and for the size and the thickness of perovskite we grow, it's like it's around the wavelength. Usually we see is around 500. Maybe 25 nanometer, or even sometimes it's around 530 nanometer. So,
how does it relate with the wavelengths of the condensate you observe? Is it blue shifted or red shifted, or it's nearby the energies of the condensate?
So the exciton resonance we in our model is like 2.4. The 2.408 millimeter. The lasing energy is around, sorry, here you can see is 2.28. Here is a electron volt. It's smaller than I usually see.
And also there is a nice experiment which you did when you play with the voltage, and you show that you can tune polariton lasing the wavelengths nicely in your system. I'm wondering if you see any difference in the threshold if you tune when you tune the.
Yes, I see.
What's the difference? Where do you see the maximum and the minimum of the threshold?
The minimum threshold, I believe, is around. Sorry, I will check with my students. It's not changed too much. I mean, the minimum, but in sometimes, for example, in this experiments, we see when the voltage is like larger than 4.5 volts. Really, we see the threshold seems to be increased. I mean, sometimes we cannot see condensation or lasing of polaritons when the voltage is larger.
Well, okay, in other words, if the mode, the polariton mode is higher in energy, you can see lower threshold to higher threshold.
Sorry, here we do not measure the specific threshold for, like we compare, we do not measure this threshold from I to P. I think we will check. I mean, we will check, but it looks like it's really the threshold is very sensitive. I mean, to the voltage. Really, it's like sometimes you have to increase or sometimes you have to decrease power. You mean to see the polariton condensation of the different energy level.
Okay, thank you very much. Thanks, very interesting.
Thank you, Anton. Jacek from Warsaw didn't have a chance to ask so far.
Okay, can you hear me?
Yes, we can hear you.
Yes.
Okay, hi, I do appreciate your results, and it's quite interesting that there is another group which is doing very similar research. So I'm very happy to have another group and in this field. I have a just question concerning the strong coupling. If you can back to the slide number 3. Okay.
Number 3.
Number 3, yes, at the beginning of your presentation. So I was late because there was an accident when I was traveling to.
Sorry, you mean this one?
No, 3. The 3 is when you show the results of this one. Then
This one?
yes. Then as you see, there is a change of the dispersion relation in the subsequent resonances due to the presence of exciton. But this change, in my opinion, is due to the fact that there is an abrupt change of refractive index close to the excitonic resonance. And since you increase the refractive index, also effective mass of the mode increases. So closer to the resonance, you have higher refractive index, so you observe this kind of behavior, and you can, for instance, by Berman method, you can, even without strong coupling, just by having this dispersion, you can observe such curves. Then my question is about the. It will be one question, but I would like to show this question using your slides. So the question is on slide 11.
11.
Yeah. Oh no. Sorry, 8. My question is that when you prepare your cavity and you fill it with liquid crystal, have you used the rubbing or ordering layer for liquid crystals in order to be sure that all the molecules of liquid crystal under the external electric field, they change their orientation and in order, or how you order the liquid crystals?
Sorry, you mean in this slide?
On the right side, you have the scheme of the cavity, yes. And there is a PMMA on the top mirror. Yes. But on the side of the perovskite, do you have an ordering layer, or just the liquid crystal just is on the top of the perovskite?
No. We do not. We are, initially, we see your paper on science, and we are very excited about this field. So initially, we really follow your procedure to fabricate the liquid crystal, and we want to see whether we can observe strong coupling, between WS2 monolayer. So, but we never see strong coupling. So we change the procedure of the fabrication of this liquid crystal macrocavity. So we just use the PMMA without using other layer to fabricate the macrocavity.
Okay, so the liquid crystals on the surface of the perovskites are just oriented by the.
No. Sorry. I mean, we transfer the perovskite onto the surface of the DBR, and then we put the PMMA layer. So the liquid crystal does not attach the perovskite.
Okay, so there is another PMMA layer at the top. So then on slide 11, there is this double layer of this mode, which, as I said, one at room temperature, one has to be careful about this strong coupling, I believe, because this is the problem with this refractive index. So maybe this is this horizontal vertical splitting of the modes, just because the anisotropy of liquid crystal introduces to the cavity. So that was my long question. So because the strong coupling is something which typically we would like to observe, like the change of the curvature at high K, high momentum. but in those systems, this is similar to the system with parallel, that there is a change of the refractive index that's due to the dispersion because of the presence of exciton. So there's a question about how you're sure about the strong coupling in the system.
You mean so in this slide, your question is how do we make sure this is I mean the LP1, LP2, LP3, and LP4 is it really is strong coupling, right? Am I right to? You mean in this?
Okay, maybe Barbara has a similar question, so I will pass the voice to Barbara. I'm so, yes.
No, I just had the question concerning if we are at this slide. So do you see the same coupling strength for both LP1, LP2, LP3, and LP4, or the Rabi splitting is different for all of the bands?
The Rabi splitting here is is gotten from the fitting. So in the fitting, we use the same Rabi splitting for different branches.
So I have another question, but I don't know if I'm in a row, so I will ask. I will wait.
No, go ahead. Since you have the microphone, please go ahead.
Yeah. No, because I had the question about the macroscopic coherence, the results that you show with the Michelson interferometer.
Sorry.
Yeah.
It means,
yeah, that's on this. Yeah. The interference fringes. Because there you have my first question is it the retroreflector or it is just the rotation of the image? Because the retroreflector makes us the symmetric image versus the center of the symmetry. And here you wrote that this is 180 degree, just the rotation. And the second question concerning this would be how large this laser spot you can make, because here you have 5 microns. So, and previously you said that you can make also large spots. So how big spots you can make to see the interference fringes and how homogeneous they are. And if you can probe the coherence or the correlation function for the different distances.
Firstly, this one is from a reflector. It means the laser beam is go through the it's like the how to say is I think we got the interference fringes from the first is the first one. I mean you mentioned in the first question. This is one. Secondly, the laser spot is very large because we found if we the pulse laser, the spot size is small. Really, it can burn destroy the perovskite. So the spot size of the laser spot of the femtose laser spot is very large. The size of the perovskite is because when we transfer there are many perovskite macroplates. So this one is the size around 50 micrometers. But it looks like really it's leasing. I mean the condensed polariton looks like localized in a small region in around 5 micrometers. So other area really we do not see the signal. I mean from the macrocavity above the threshold. So I think maybe we believe maybe there are some the perovskite macroplate is not very homogeneous. This is the reason. I mean maybe when we transfer the perovskite macroplate onto the surface of the GBR, maybe this can bring some problem for the homogeneous. I mean, on the surface of the perovskite, I think.
Okay, so let me just sum up if I understood correctly. So this is the image with the femtosecond laser. So this is pulsed excitation. The excitation spot is large, but anyway, you see the signal only from this 5 micrometers.
No. Above threshold, we see the, we can see all the, the perovskite microplate, we will see it can emit light, all of the area, all the perovskite microplate, we can see the signal. We can collect the PL. But above threshold, it looks like, we see the condensed area is smaller than the perovskite microplate.
Thank you.
Thank you, Barbara. So Tamsin was next.
Yeah, could you go to the slide that has the femtosecond plus the CW excitation? I don't remember what slide number it was, I'm sorry.
Yes, sir.
Yeah, so you have a additional blue shift when you add the CW laser, and this is above threshold, I take it, but you have a continuous blue shift anyway. So if you are below threshold, do you see the whole dispersion blue shift when you add the CW?
We didn't measure this. No, we didn't measure this when the pulse laser, the power for pulse laser is below threshold. I think we will try to measure this.
And in addition, the CW laser, is this modulated with an AOM? Because obviously this would cause quite a lot of photo bleaching on your organic sample.
No, we do not use any AOM because the power is very low. You can see the 50 microwatts. So we do not use AOM to, I think there should be no heating, because the power is very low, I think.
Okay, thank you very much, sorry.
Thank you, Tamsin. Paul, we're coming back to you.
Thanks. I was just wondering, wants to come back to this thing of these small spots and the emission being from small localized regions.
Okay, yeah.
I guess I wondered, do you have real space images of the condensate, and is what you see consistent with this just being condensates forming that are localized by disorder, or might there be something else going on?
This is a very good question. This is the real space imaging of this of the polariton condensate in this microcavity. In other, we also fabricate other microcavity where there is no liquid crystal. We usually observe polariton condensation is trapped in some very small, disorder induced potential traps. We see really very, very small red spot in the perovskite microplate. Sorry, I didn't show this result, because this microcavity, we do not use liquid crystal. But in the experiment, really, in some perovskite microplates, we really observe, we believe really polariton condensate is trapped, in some disorders, I think. But in this microcavity, we believe is, I'm not sure, but I'm not sure about this question.
Okay, thanks. I guess just to follow up, so the spots you see, are they kind of always in the same place on a given sample, or is there any time dependence of the?
In the fixed parallel microplace is always at the same position. Right. We also in other microcavity we do really single shot measurements. It looks like the position is not random. It's not this microcavity, not this one, but other microcavity with when there's no liquid crystal, we do not observe any random localization of this polariton condensate. But we will try to see any Hobern effect or something else in the future.
Done. Thanks.
Okay. So I see that we don't have any more questions, and we have already passed the 1 hour mark. I know that it's very late for you, Tianjin. So thank you very much for coming here today. Thank you all for joining this webinar and all your questions.
Thanks.
So we will send you a link with your presentation, and we can follow up the discussions over email.
Oh, sure, no problem. I'm very happy for the invitation, and we can discuss later about this very, very exciting direction you developed. Thanks a lot.
Okay, thank you for coming, and thank you everyone for joining us today. Have
Thanks.
a good day.
Thanks.
Bye, everyone.
Bye.
Okay, bye.